Good afternoon. We are going to see the theory part today that is related with a solution of differential equation. That is linear differential equation. First, we will go with order 1. So now we have equation that is dy by dx plus py is equal to 0. So we have this is order 1. So now here we have P and Q. These are functions of X. So we have P and Q are functions of X. And so multiply both sides by e raised to p dx. And we have e raised to p dx into dy by dx plus py equal to e raised to p dx. Now you can see this, what we are going to get from this actually. So if I will multiply by this e raised to px to these two terms, then what we will get actually? So we have e integration p dx into dy by dx plus py into e raised to p dx. Now if you will see carefully, then we can have this as d dx of y into e p dx. This value we have, or this expression we have, derivative of y e integration p dx. Now how big you can see this? So we have first, we have this will be u, we have this will be v. So we have v as it is, derivative of u, so that is dy by dx, plus we have u, derivative of u, so we have v as it is, sorry, u as it is now, so y as it is into d dx of e integration p dx. Now you can solve this, so we can have e integration p dx into dy by dx plus y into derivative of this will be e to the power x will be as it is into d dx of integration d dx of integration e, p dx, because we have e to the power 4x. If we will find derivative of this e to the power 4x into d dx of that power 4x, and therefore d integration of p into dx. Now this integration and derivative gets cancelled, and we will get it as e integration p dx into dy by dx plus p into y into e integration p dx. And we have this term, we can see we have this term, and therefore we have this term becomes d dx of y e integration p dx. And this right part will be as it is, we have q and we have multiplied it by e integration p dx will be as it is. Now we will take derivative on both sides, and from this we will get left side we have actually taking integration on both sides. Then we will have this derivative d dx and this integration get cancelled, and this becomes y e to the power p dx, and which is equal to, we have integration of this right part. Now in this e integration p dx, this is known as integrating factor, and this is your solution of the differential equation to order 1. So likewise, we have to solve this problem. So in problem, we will directly use this for the solution. Then we have linear higher order differential equation with constant coefficients. So coefficients a1, a2, a3, a4, we have this as constant. Now we can have this as nth power, you can nth order, you can say. And degree we have 1 only. So now we will go with symbolic form. So we will have this. So we are going to just replace d dx, that is by capital D. Now we can have auxiliary form or characteristic equation in this fashion. Now in this, we are not going to consider Q and we have equation in this way. Then solution of our equation we have complementary function plus particular integral. Now y is equal to CF plus PI. So the solution of this left part, this will gives me complementary function, and that is of right part will gives me particular integral. And the solution we have sum of these two. And then if my value of Q is 0, then my this symbolic form I can write it as auxiliary form by just replacing y. And if Q is 0, then my particular integral is 0. So if Q is 0, then solution is only CF, because if Q is 0, then my particular integral will be 0. And equation will be y equal to CF. Now we will go with complementary function. Now we have auxiliary form in this fashion, and then we have actually three cases, or we can say three types of roots. So we have n roots for it, and then we can have first roots are real and distinct. What will happen in this case? So we can have this when roots are real and distinct. My complementary function will be C1 e raised to m1x plus C2 e raised to m2x. So I have solution that is roots of these are m1, m2 and likewise. And we have m1 is not equal to m2. Then we have case 2 where my roots are real and equal. Roots are real and equal. So we are talking about first two roots, I can say here. First two roots. And then we can have likewise. So now when two roots we can say are equal. So now here I can write I have m1 equal to m2 equal to m. And from this I will get this equation C1 plus C2x e to the power mx plus C3 e to the power m3x, and then likewise. Then from third part onwards, we have same in both cases. Now third we have that is roots are imaginary. So third we have roots are imaginary. So roots are imaginary. And then we can go with this third case and we will get it as e raised to alpha x in bracket c1 cos beta x plus c2 sin beta x. And likewise, we are in position to calculate complementary function. So likewise, we have to solve the problems. That is when my particular integral is 0. And when we have particular integral 0, if q is equal to 0, then particular integral is also equal to 0. Now we will see how we will solve this. So now we have, let us first d square minus 5d plus 6. Now if we will see this, then we have the equation d minus 3, d minus 2 equal to 0. You can see this, I have solved this actually. And from this we are going to get d equal to 3 and d equal to 2. Or I can write this as m1 equal to 3 and m2 equal to 2. And we will put in this equation, we have two roots only. So my complementary function will be this portion only. And m1 I have to put as 3 and m2 I have to put as 2. And I have this as solution of linear differential equation to degree 1. Then we will go to case 2 when roots are real and equal. Now in this we have d square minus 6d plus 9 equal to 0. And actually we have d minus 3 whole square. And that is equal to 0. You can see over here. And then we can have d equal to 3. And that is both values. So I can write it as m1 equal to 3 equal to m2 equal to m. And therefore we have to put this m that is equal to 3, and we have complementary function only this part. So we have c1 plus e2x e to the power 3x. So this is my complementary function, and as q is 0, so I have this as solution of the differential equation. And then I have third, where I have cf that is equal to c1 cos beta x plus e2 sine beta x e to the power alpha x. Alpha we have that is real part, and beta we have imagined. Alpha real and I beta we have this as imaginary. And then likewise we have to solve this. So we can have this. Now we know how we will get this value of d, so that we can find minus b plus minus root of b square minus 4ac upon 2a. And now here I have b equal to minus 4, a equal to 1, and c equal to 9. And substitute these values. We are going to get now minus minus plus 4. This will be 16 minus 36, which will be minus 20. And then we will have this value. Now we will take from this, that is minus 4 into 5. 4 we will take outside, and that becomes your 2. Now from this we can take 2 outside. 2 plus minus root 5 upon 2. Now these 2 gets cancelled, and we have this as 2 plus minus. This actually we have root 5i. Oh, sorry, 5i, because I we have minus I we have root of minus 1. So 2 plus minus 5i. And then we will put it e raised to, because this is alpha equal to 2 and beta equal to 5. And then from this we will get e raised to 2x c1 cos pi x plus c2 sin pi x. And this is my complementary function, and that is for third case. So likewise we have to solve the problems that is related with your solution of linear differential equation. But in this we are with order 1 and order 2, provided q is equal to 0, or we have that is particular integral that is equal to 0, and then only we can solve this problem. So this is all about your solution of linear differential equation. So thank you.